Hello dear students, welcome to mathematics class. This is Prakash Bankar from Tunga Degree College, Jamkandi. In this class, we are discussing about the mathematics paper 1 of BSc 5th semester. The title of the paper is Real Analysis. So here it is the syllabus of the real analysis. In this, the first unit is Riemann integration, and this unit consists of partition of an interval, the upper and lower Riemann sums and Riemann integrals, necessary and sufficient conditions for integrability, algebra of integrable functions. In this Riemann integration, we are not actually integrating the given function by applying the standard formula, but we are evaluating the same integral by finding Riemann lower integral and Riemann upper integral. Let us consider a function f from the closed interval a to b to the set of real numbers. Let us consider the graph of this function as here. So now this is the graph of the function f, and here it is the lower limit of the interval, that is a, and this one is the upper limit of the interval b. Now to find the integral a to b f of x dx, it is equal to what? Whatever the area lying under the curve will give the value of this integral a to b f of x dx. To find this area, we are dividing the interval a to b into the rectangular strips. So here the first point is a, which is can be considered as x0, then x1, x2, x3, so on up to xn minus 1, and xn is nothing but b only. Now regarding these points, draw the straight lines which is perpendicular to x axis and cutting the given curve. Now here it is the first line, second line, third line, and so on up to this is the n line. Now if you want to find the area, here you have to consider the rectangular strip which is at the end of the first line A, and then continue in the similar way. Now we will get some approximate value. To find the exact area, we need to further divide the interval a to x1 as some other point, let it be y1, and this will be y2, and this one is y3, y4, like that. Now the width of each rectangle will be reduced as before. Then we are finding more appropriate area. So this is the general method of integration, means that is the geometrical interpretation of the integral a to b f of x dx. Now let us discuss some basic definitions in Riemann integration. So here these are the definitions. The first one is partition. Already we told that partition means, in general, the partition is dividing. So here splitting of an interval is called as partition. In mathematically we are splitting the interval. Suppose here the given interval is a to b, we are dividing this interval into the smaller parts, that is x1, x2 up to xn, and in the next we are dividing the same interval as y1, x1, y2, x2, y3, x3, means the area, the width of the rectangle will be smaller. So here splitting of an interval is called as partition. So here the mathematical definition is, let I is equal to the closed interval AB, then finite set of points which is denoted as P is equal to x0. x0 is nothing but the lower limit of the interval AB, and x1, x2, x3, so on up to xn. Here xn is nothing but the upper limit of the interval AB, such that here the condition to divide that interval is a must be equal to x0, that is the first point of the division, and then x1, that x1 must be greater than x0, and the third point is x2, that should be greater than the second point, and so on. The last point is xn, which is nothing but b. So here let I is equal to the closed interval ab, then the finite set of points p is equal to x0, x1, x2, so on up to xn, such that satisfying the condition that x0 must be less than x1, x1 must be less than x2, and so on, xn is called partition. So therefore, any interval, if we are dividing that, satisfying this condition is called as partition. And then the n plus 1 points, here the number of points is equal to n plus 1, because the first point is x0, x1, x2 up to xn, then the total number of points will be n plus 1. So these points are called as partition points of P. In general, any partition can be denoted as the capital P. And the next point is the closed intervals. So there are several intervals, and that first one is I1. I1 is the first closed interval consisting of the points x0, x1. So these are the first two partition points of P. x0 is the first point, x1 is the second point, and the closed interval consisting of these 2 points is named as I1. And the next one is I2. I2 is from x1 to x2, and so on. IR, in general rth interval, IR is equal to xr minus 1 to xr, and so on up to the last interval In, which is equal to xn minus 1 to xn. So these intervals are called as segments of partition. Our total partition is from A to B, and that we are dividing like this: x0, x1, x2, so on up to xn. And again, this total partition is consist of the segments. Each segment is of length x1 minus x0 is the length of the first segment, x2 minus x1, that is the length of the second segment, and xr minus 1, that is the length of rth segment, and the length of the last segment, that is In, is given by xn minus 1. So these are called as length of the segments. Now in the next point, the length delta r. So it is the length of the rth subinterval. Here the rth subinterval is nothing but from xr minus 1 to xr. So therefore the length is nothing but the difference of upper limit and the lower limit of the given interval. So therefore delta r is equal to xr minus 1 is called length of subinterval. Now the greatest of delta r's, after finding the length of all these intervals, whichever is greatest, that is called as norm. That is norm, and this is denoted by the symbol norm of P. Here it is the mathematical definition. Norm of P is equal to maximum of delta r. Here r is from 1 to n. Delta 1 means that is the length of the first segment I1, and delta 2 means that is the length of the second segment. Delta 3 means that is the third segment, delta 3 from x2 to x3. So therefore, which is the maximum value of all these delta r's, that is called as norm of the partition P. And now refinement of partition. If P1 is said to be the refinement of P, if P1 is the superset of P, or P is contained in P1. So here, if you divide the interval AB as x0, x1, x2, so on up to xn. Again, if you want to divide this set into the further partition, let it be x0 star, x1 star, x2 star, and so on up to xn star. So these are the points of the second partition. Now let us consider this one as P1 and this one as P. Always P1 must be the larger than the P. Whichever the larger partition is there, that partition is called as refinement of the partition. Now the next definition is common refinement. If P1 and P2 are the two refinements of P, means already P is a partition and again we are dividing the same partition into two refinements. One is P1 and the another one is P2. So if you take the union of P1 and P2, then that union of partitions is called as common refinement of P. So these are some basic definitions of Riemann integration. The first one is partition and the next one is segment of the partition, length of subinterval, then norm, refinement of partition, common refinement. So these are the fundamental definitions of Riemann integration. Let us discuss with Riemann sums. There are two types of Riemann sums. The first one is lower Riemann sum and the second one is upper Riemann sum. So these are the two types of Riemann sums. One is lower Riemann sum and the second one is upper Riemann sum. Let us discuss the first one, lower Riemann sum. So here it is lower Riemann sum, which is denoted as LPF, and lower Riemann integral. Simultaneously we are defining the two definitions. One is lower Riemann sum and the other one is lower Riemann integral. So now here also consider a function f from the closed interval AB to the set of real numbers R. Now it is the graph of the function f. So here A is the lower limit of the interval AB, B is the upper limit of the interval AB, and we are dividing that closed interval AB into some partition. The first point of the partition is x0, x1, x2, so on up to xn minus 1 and xn. And now draw the perpendicular lines from x axis to the graph of the function. So these are the rectangular strips, and the first rectangular strip is having the length m1, this length is m1, and the second is m2, m3 and so on mn minus 1 to mn. Now we are drawing the perpendicular lines from the first line to the second line to the third line to the fourth line and so on up to xn minus 1th line to xn. Then you will get some rectangular strips. Now to find lower Riemann sum, here we need to find the area under the curve f. So here m1, m2, m3, so on up to mn. So these are length of rectangles. These are the lengths of the rectangles. Then to find the area of a rectangle, we need length as well as breadth. And how to find the width of the rectangle? So it is the length, then here it is the width or breadth. The width of the first rectangle is given by x1 minus x0, and the second one is x2 minus x1, the third one is x3 minus x2 and so on. The width of the last rectangle is given by xn minus 1. So these are the widths of rectangles. And then now we got length as well as width, then the area can be evaluated easily. Now the area under the curve is given by LPF. Whatever the area which is lying under the curve is called as LPF. LPF, this is because we are finding the area of this curve by considering first the minimum value of the interval. So, from point A to B we are drawing the rectangular strips. So, that is why it is lower Riemann sum, and this is LPF. So, here the length of the first rectangle is length into breadth, that is m1 into x1 minus x0 plus, because we need to add all the areas of the rectangles, and the second one is m2 into x2 minus x1 plus m3 into x3 minus x2, and so on up to mn into xn minus 1. So, here this is the total area bounded by the curve f with the x axis. So, therefore, it is the LP of m1 into x1 minus x0 plus m2 into x2 minus x1 plus m3 into x3 minus x2, so on up to mn into xn minus 1. Now, this summation can be denoted by using the sigma notation, that is summation over r is equal to 1 to n mr into xr minus 1. So, it is the sigma notation of the above line, which is the sum of the areas of the rectangles. So, here r is taking the values from 1 to n. So, now if you put r is equal to 1, then it is m1 into x1 minus x1 minus 1, that is equal to 0, nothing but x0. Then if you put r equal to 2, then it is m2 into x2 minus x1. Like that, you will get the last term if you put r is equal to m. Now, this can be further simplified as summation over r is equal to 1 to n mr into delta r, where delta r is the length of rth subinterval or rth segment, that is equal to xr minus 1, where these 2 points are from the interval IR, which is equal to xr minus 1 to xr. So, it is the rth segment or rth subinterval, and delta r is the length of rth subinterval. So, therefore, it is the LPF, Riemann lower sum, LPF. So, here delta r is the length of rth subinterval, and mr, small mr is the infimum of the function f of x, where x is from the rth subinterval, that is x lies between xr minus 1 to xr. So, therefore, here mr is the infimum and delta r is the length of the rth subinterval. Infimum means that is the GLB, greatest lower bound, GLB of the function. Here the function is varying from the point A to B. In this area, whatever the GLB is there for the length of the rectangular strips, that is nothing but mr, and it is the formula to find the lower Riemann sum and lower Riemann integral. Lower Riemann integral can be given by using the formula lower Riemann integral. So here already we found lower Riemann sum, and regarding the lower Riemann sum we are defining the lower Riemann integral. So here lower Riemann integral can be given by supremum of LPF. Supremum means that is the least upper bound, LUB. Whatever the upper bounds are there for a function f of x, among that we are choosing the smaller one, that is the least upper bound. Now after finding all the Riemann sums, we need to find supremum of them, that will give the lower Riemann integral, and here the symbol is bar a to b f of x dx. So this notation is for lower Riemann integral. The next is upper Riemann sum and upper Riemann integral. Here also consider the function from the closed interval a b to the set of real numbers r, and now this graph is for the function f. As in the previous case, that is lower Riemann sum, we are finding the same function which is f, and the area will be same because we are considering the same function f, which is having the domain the closed interval a b and the codomain is the set of real numbers. But here only the difference is we are finding the rectangular strips regarding the highest value of the interval. In that we are concentrating on the lowest value, so that is why it is lower Riemann sum or lower Riemann integral, and here we are first considering the highest value of the interval, that is b. So therefore we are finding the first rectangular strip as at the point b, next xn minus 1, xn minus 2, xn minus 3 and so on up to x0. X0 is nothing but the initial point a. So here capital M1 is the length of the first rectangular strip, then M2, M3, so on up to Mn, capital Mn. So these are the lengths of the rectangular strips, and again width will be x1 minus x0, that is the first rectangular strip, then x2 minus x1, x3 minus x2 and so on up to xn minus 1. So therefore these are the required data, which are length and widths. Then to find the area under the curve is given by UPF. UPF is nothing but upper Riemann sum, and we are considering this as the upper Riemann sum because we are considering the rectangular strips from the highest value to lowest value, that is from b to a, and initially we were considering that from a to b, that is the lower Riemann sum. So therefore it is equal to m1 into x1 minus x0 plus m2 into x2 minus x1 plus m3 into x3 minus x2 and so on mn into xn minus 1. And again in the summation form we can denote that as r is equal to 1 to mr into xr minus 1, and more conveniently we can write this one as from r equal to 1 to n mr into delta r. Again delta r is the length of the rth subinterval xr minus 1, and that is the interval is ir equal to from xr minus 1 to xr. xr minus 1 is the lower limit of the interval and xr is the upper limit of the interval. And here capital MR is supremum of the function f of x in the interval xr minus 1 to xr. In the previous case it was infimum, that is the lower bound, and here it is the upper bound, that is nothing but LUB, least upper bound of the function f of x in the rth sub interval, and this sum is nothing but upper Riemann sum. And next, upper Riemann integral. Upper Riemann integral. So it is given by infimum of UPF. Infimum is nothing but greatest lower bound of all the Riemann upper sums, and here the symbol is integration over a to b bar f of x dx. So it is the upper Riemann integral which is given by infimum of UPF, and the integration of this function can be given by integration over a to b bar f of x dx. So here it is the comparative study of lower Riemann sum and upper Riemann sum. Lower Riemann sum is given by LPF, which is equal to summation over r is equal to 1 to n small mr into delta r, and upper Riemann sum is UPF, which is given by summation over r is equal to 1 to n capital Mr into delta r, where small mr is infimum or GLB of the function f of x in the interval xr minus 1 to xr, and capital Mr, that is the supremum or LUB, least upper bound of the function f of x in the interval xr minus 1 to xr, and this delta r is nothing but length of the rth sub interval. In both the sums this delta r is common, the delta r is equal to xr minus 1, which is the length of the rth sub interval IR, which is equal to xr minus 1 to xr. And the next one is lower Riemann integral, and it is the symbolic notation of lower Riemann integral, that is integration over bar a to b f of x dx, that is equal to what? Supremum of LPF. So here this lower Riemann integral is the supremum of all the lower Riemann sums. So the first lower Riemann sum is given by small m1 into delta 1, second lower Riemann sum is m2 into delta 2, and so on mn into delta n. Among all these sums, which is the supremum, means least upper bound, that will be the lower Riemann integral. And similarly, in case of upper Riemann integral, the symbolic notation is integration over from a to b bar f of x dx, which is equal to infimum of UPF, means it is the lower bound, greatest lower bound of all the upper Riemann sums. So therefore, this will give the comparative study of lower Riemann sum, upper Riemann sum, lower Riemann integral and upper Riemann integral. The next definitions are Riemann integrable function or R integrable function. A function f from the closed interval a to b to the set of real numbers is said to be R integrable or Riemann integrable function if lower Riemann integral and upper Riemann integral are same. That is, integration over a bar to b f of x dx must be equal to integration over a to b bar f of x dx. So this is the condition for a function f to be R integrable. So it is the necessary and sufficient condition. From a bar to b f of x dx must be same as a to b bar f of x dx. And the next one is oscillatory sum. Again consider the same function, let f from the closed interval a b to the set of real numbers, be a bounded function, and this is the partition P is equal to x0, x1, x2, so on up to xn is a partition of the closed interval AB, and let small mr and capital Mr be the infimum and supremum of the function f on the interval IR xr minus 1 to xr. The small mr is the infimum of the function f in this the interval, and capital Mr is the supremum, means upper bound and lower bounds of the function f in this interval. Now consider the difference of upper Riemann sum and lower Riemann sum. By definition of UPF and LPF, we can write that UPF is equal to summation over r is equal to 1 to n capital Mr into delta r minus as it is, then LPF is nothing but summation over r is equal to 1 to n small mr into delta r, which is equal to here that summation and delta r in common, then summation over r is equal to 1 to n mr minus mr whole multiplied by delta r. Here the difference of supremum and infimum can be denoted by the symbol OR and delta r as it is. So therefore, r is equal to 1 to n OR into delta r. So this is called as oscillatory sum. The summation over r is equal to 1 to n OR into delta r, it is nothing but the difference of UPF and LPF is called as oscillatory sum, and the term OR is nothing but oscillation of the function f in rth subinterval IR, which is equal to xr minus 1 to xr. So these are the two important definitions, Riemann integrable function and oscillatory sum. Let us discuss one important result. So for that result, let us consider the partition P, which is equal to x0, x1, so on up to B, that is nothing but xn, where A is the initial point or the lower limit of the interval AB, and B is the upper limit of the interval AB. And now consider the sub intervals. First one is I1, that is from x0 to x1, I2, x1 to x2, I3, x2 to x3, and so on IR, it is from xr minus 1 to xr, and finally In, that is from xn minus 1 to xn. So already we know that delta r, that is the length of rth subinterval, which is given by xr minus 1. And similarly, if we want delta 1, that will be equal to x1 minus x0, which is equal to x1 minus a, because x0 is equal to the lower limit, that is a. Then delta 2 is equal to x2 minus x1, delta 3 is equal to x3 minus x2, and so on. Delta n is equal to xn minus 1 or b minus xn minus 1, because xn is equal to b. Now the result is summation over r is equal to 1 to n delta r, means if you take the sum of lengths of all the sub intervals, then what will be the length of that total interval. So here it is nothing but delta 1 plus delta 2 plus delta 3 and so on up to delta n. Now the delta 1 is equal to x1 minus x0, that is nothing but x1 minus a, plus delta 2. Delta 2 is x2 minus x1 plus delta 3 is x3 minus x2 and so on. Delta n is xn minus 1, which is nothing but b minus xn minus 1. So here now we can cancel out the terms with same magnitude and opposite sign. Here x1 is negative and the x1 is positive, means these two terms will get cancelled. In the next one, x2 is positive, x2 is negative. Here if x3 is positive, in the next difference that x3 will be negative, that will get cancelled. And finally minus of xn minus 1 and the previous plus xn minus 1 will get cancelled. Only remaining terms are, here it is minus a, and in the last difference it is plus b, that is nothing but b minus a. So therefore, if you take the lengths of sum of all the sub intervals, then it is giving that summation over r is equal to 1 to n delta r is equal to b minus a. So it is the standard result which you are going to use in the successive theorems.